Next up, we have Rico Landman, who's going to be talking to us about SUPPPPRESS. There you go, and then stand near the X.
This works. Test, can you hear me? Yes. Great. All right, it's my pleasure to talk to you about the SUPPPPRESS project, where we're trying to develop low-leakage liquid crystal coronagraphs. And yes, there's 4 Ps, I'm not stuttering, and I have absolutely no idea what they actually stand for. I'm presenting on behalf of the entire SUPPPPRESS team, which is a consortium of European partners from academic partners and industry. So as we look towards the Habitable Worlds Observatory, these are the kind of images that we want to see. And I'm not involved in determining the science cases, but I'm interested in what they mean for the coronagraph requirements. So what do we need from our coronagraph to get these sites? So one of the things that we want is we want to be able to see these Earth-like planets, and we need 10 to the minus 10 contrast, or even better, as Chris told this morning. So we need close to optimal coronagraphs with high throughput, small inner working angle, and robustness to lower their aberrations. And preferably, we would use coronagraph to also facilitate focal plane wavefront sensing for dark hole maintenance. Then we need a broad operational wavelength range to actually detect the molecular absorbers in the atmosphere of the planet, so we can search for biosignatures. And we would also like to do polarimetry, so we can, for example, see ocean glints and rainbows on these planets. So it would be nice if our coronagraph could work with polarimetry. So one of the leading candidates, one of the best performing candidates is the vortex coronagraph. And I really like this illustration by Dimitri, where you see that for an on-axis star, whoa, this is, yeah. If it falls on a singularity, it gets this phase ramp, and the light gets distributed outside of the pupil, where it can subsequently be blocked by a Leo stop, while for an off-axis source, it will not get this full phase ramp, and it actually passes through the Leo stop. So on the right is a study by Russ Balikov showing the inner working angle of these various coronagraphs, wrong button, as a function of stellar diameter. And this part is inaccessible by physics, and we see that the vortex coronagraph is quite close to this theoretical limit, especially for monolithic, non-segmented apertures. So one way to make these vortex coronagraphs is with using liquid crystals. So the problem with just making a phase ramp is that it's very chromatic. So it will be a nice vortex for one wavelength, but for another wavelength, it will not be. So to make it achromatic, we can use geometric phase. I'm not going to explain what geometric phase, how that exactly works, because it will take me full 12 minutes, and I barely understand it myself. So you just assume that this is this magic optical device which can apply the same phase to independent of wavelength, the same phase shift independent of wavelength. And the advantage of that is that it's broadband. It's been developed here at JPL and for a long time, so it's quite a mature technology where we know how to use it. We've used it in cryovacuum, so we know that it will survive. And since we're already manipulating polarization, it's very easy to include polarimetry with it. However, the disadvantage is that if your component is not perfect, which is not, you will get some polarization leakage and you will need to do polarization filtering. And this, of course, is not what we want because we will lose 50% of the planet light. Secondly, the vortex struggles a bit with segmented apertures. So we have a long history of making these patterned liquid crystal optics for various applications. So the cool thing is about this, we can write arbitrary patterns, so we can basically make free-form face plates, and these have many different applications. So we've used these over the past 10 plus years for coronagraphy, for wavefront sensing, interferometry, even for art, and many different applications. So we used this with the University of North Carolina, and later Imagine Optics. And then about 3 or 4 years ago, we suddenly didn't hear from them anymore, and they got bought up by a certain American tech company. Luckily, we got the license for astronomy. They got licensed to a company in Japan, ColorLink Japan. So we were super happy that we could start making liquid crystal optics again. So we went there, tried to make a vortex coronagraph, super excited, and what we got was this. Well, even if you've never seen a vortex, this is not what we want to see. Yeah, so this was about a year and a half ago, and we were like, okay, we can go home, we can stop, but luckily not. So right now we've significantly improved the manufacturing quality, and we can now make good vortex masks. And I really want to shout out the engineers and people at ColorLink Japan for their hospitality and all their hard work in improving this manufacturing quality. We've come a long way in this year and a half. So this has been a close collaboration between Nova and ColorLink Japan. We've visited them multiple times. They've come and visited us. Yeah, we've made huge strides in the manufacturing quality. And the good thing about this is that we now are involved in every step of the manufacturing pipeline. So we have much better insight in what's actually limiting this manufacturing. Well, before we just got the optics, we used them. There was some weird things with them. We didn't really understand what was actually going wrong. So now we have full control over the entire pipeline of the manufacturing. So now, and then we have 2 years ago, we started the ESA-funded SUPPPPRESS project, where we try to improve the technology readiness level and space qualification of these vortex coronagraphs, specifically focusing on multi-grating vortex chronograph, which I will talk a little bit more about later. So yeah, I won't go into all the details about the manufacturing, but there's a few important quantities. The most importantly are the patterning quality, so how well is it actually vortex, the phase, and the polarization leakage, which I already talked about before. So the patterning quality, we would like this. So here I show the retrieved fast axis from metrology for a charge 6 vortex, and we would like this to be a perfect vortex. So if we subtract off the perfect vortex pattern that we would get this kind of error. I've done simulations for this, and this gives about a 5 times 10 to the minus 8 contrast, about at 3 lambda over d, before EFC. You can correct this with EFC, but it's a little bit difficult because it will sort of show up as a polarization aberration, so you'll still have to do polarization filtering. So yeah, this is significantly better than we originally had, and yeah, we have a good grasp about the calibrations that are needed to keep this level. We're hoping to improve this further by operating the patterning machine in a stabilized environment, further optimizing the calibration procedures, or even actively controlling the polarization state. Then the polarization leakage. So we use a technique using multiple twisted retarders to obtain broadband half-wave retardants. So if you have a single half-wave retard, it will be half-wave at one wavelength and then not. So we get a lot of leakage of the central wavelength. So we use multiple layers of twisted retarders. And we did a lot of design work for this and testing. So we basically designed what we call a recipe that the engineers can follow to obtain broadband performance. And here you can see some of the results. So this shows the leakage as a function of wavelength. And we get about 3 times 10 to the minus 4 over a 10% bandwidth, and 8 times 10 to the minus 4 over a 20% bandwidth. So this is nowhere close to the 10 to the minus 10 or 10 to the minus 8 that we need for HWO. So how do we go about mitigating this polarization leakage? So for that, we can use polarization gratings. So here I show one single polarization grating, and so it's geometric phase. So if we just simply assume that we have one circular polarization state coming in, then almost all the light will be diffracted in the first order. If you would have the other circular polarization, it will be diffracted the other way. However, we have about 10 to the minus, less than 10 to the minus 3 leakage here, which we do not want. However, if we then add a second grating, the main beam will be diffracted back on axis again. And the leakage, most of the leakage, gets diffracted off axis. So now we have 10 to the minus 3 times 10 to the minus 3 leakage. So we're already at 10 to the minus 6. You can repeat this trick one more time. Then we make a triple grating vortex. And then you're close to the 10 to the minus 10 that's needed. So what we actually do is we combine a grating with a vortex into what we call a fourth grating, which you see on the right. And we glue this together with another polarization grating, for example. And then what you get is that both polarization states just pass through, while most of the leakage gets diffracted off axis, so you reduce the polarization leakage. You can actually separate these two, and then you can get both PSFs in both polarization states, and you can do polarimetry and wavefront sensing. So this is a manufacturer's component. This is a fourth grating on the left and a grating in the middle. And if we glue these together, we get a vortex again. So that's the beautiful thing. The gratings cancel each other out, and you get a vortex back again. So how are these performing at high contrast? So we did some high contrast tests at THD2 bench in Paris, and these are some of the first results. So we noticed we had to circularly polarize the input beam. And the reason for this is probably because of imperfections in the mask, which show up as sort of polarization aberrations, which you cannot correct for with EFC. So we reach about a contrast of 2 or 3 times 10 to the minus 8 for a small bandwidth, 6 times 10 to the minus 8 for 10% bandwidth, and about 1 times 10 to the minus 7 for 20% bandwidth. So yeah, there's many different factors that could limit this. One is that we had a lot of ghost from the polarization filtering optics, of which the area rings you can still see sort of here, which can be limited in the contrast. Sorry. Also, this was a set of older components which had significantly higher leakage than the one that I showed before. Next, we did some tests on space qualifying the optics. So we did a different test, which we all successfully passed. For the UV, when we blasted it with UV radiation, we did see some decreased throughput at short wavelengths, but this can easily be mitigated with UV blocking or some other technique. I would like to note that we can also, for segmented apertures, which the vortex struggles with, we can also use a geometric phase appetizer in the pupil. So if you have a segmented aperture, you get some diffraction inside your dark hole, which you do not want. And with phase appetizer, you can shape the PSF to cancel this out. The problem with phase appetization is, again, that it's chromatic and that it doesn't work for both polarization states. So with geometric phase, you get the opposite sign for both polarization states. And because the VVC has the same, where it's a +6 charge for one polarization state and a -6 for the other, it actually works out and you can design these for both polarization states. So to conclude, liquid crystal coronagraphs are very promising for space-based exoplanet imaging. Yeah, we've made huge strides in the manufacturing quality. And we have, so with multi-grating vortex coronagraphs, we can remove the polarization leakage. Our geometric phase appetizers, we can even get them to work for segmented apertures. But so what we're struggling with at the moment is dark hole digging for both polarization states, where we don't reach the performance that we want. And we still need improvements in manufacturing quality to reach the HWO contrast. Thank you, and I'll take any questions.
Sarah?
Thank you. Hi, great talk. So you mentioned about improving your manufacturing. I was wondering if you had an idea for what your limit was to your manufacturing. Like, I imagine there's just a finite, like, step size you can have. So, like, what's that order? Is it like 10 to the minus 12, 10 to the minus 11, or lower?
So we can do it at a resolution of 1 micron pixel size. And near the vortex center, it's a little bit, because it's ill-defined, because it changes rapidly, we get central singularities of about 6 and 2 micron, depending on the charge of the vortex. But generally, the pixel size that we use is 1 micron.
Nick?
Do you have a sense of how the liquid crystal polymer will respond to a radiation environment in terms of being ionized and things like that?
Yeah, so that's the test that we did. And we tested the retardants and just the cosmetic quality and the transmission, and we didn't see any impact except for when we blasted it with UV radiation.
Thanks.
Any other questions for our speaker? Right up there. Yeah.
What do the P's stand for in suppress?
I literally have no clue. I think something is a polymer and polarization, but the rest I don't know.
Thanks.
Any other questions? All right. Actually, one up there, Dimitri.
Thank you for the talk. Is there any sensitivity to roughness scattering? Of the
sorry,
surface?
could you repeat?
Is there any sensitivity to the roughness of your plate for the scattering.
I guess it will give scattered light, yes.
I think we're out of time, or no, we have 20 seconds, if it's a fast question.
My question is, are you able to apply air coating between all your layers and substrate? And
Yes, so when we sandwich these liquid crystals, the first and last will have AR coating.
only first and last, but not in between. So
No.
as the last talk, Canadian group, they mentioned the ghost, and I believe the refraction from all those substrate could be
No,
could be
we've
problematic.
confirmed using other coronagraphs that these ghosts were still, even without the chronograph rotating it, these ghosts are from the polarization filtering optics, not from the chronograph itself.
Okay, thanks.
Great, well, let's thank our speaker again.
Thank you so much.